Hello, my name is Kevin Nguyen, and this is Lab 1 for Physics. And the lab is based on an object moving at the same speed without change in direction. So for the lab, I did both a real experiment and a computer-generated model. For the computer-generated model, I set up the coordinate system to be in the middle of the water bottle. And for my time of the video, I set it up at the 33 frame because you don't want to include your initial velocity since that's not the same, because that's the velocity that you'd use to move the water bottle, but it's not going to be the same when it's like constantly moving across the table. So I'm going to press play. And as you can tell, the position is increasing into the negative direction because it's going left, which is the negative x, and right is the positive x direction. And we don't care about y because up will be the positive y and down is negative y. But if this was, if the x-axis was reversed, this would be in the positive direction, but the numbers would still be the same. It would just be positive, but the magnitude would still increase. And then in the computer model, this is the origin, and you see the ball moving to the left. And you see this is the position versus time graph. It's a linear line. And it's going down because it's negative x direction, and the velocity is constant. And this is also the position versus time graph for the tracker. And they look very similar. But for the code here, we used a constant velocity. So I found that as negative 0.3956, which would be the velocity average between the first two positions on the real experiment. So I did negative 1.248 e to negative 2. Subtract that by 5.749 e to negative 4 over the change in time, which is 0.033. Which will be this number, and the starting position will be also the starting position on tracker. And then we can assume that force net is 0 because it's constant velocity. Since this is because of Newton's second law, final velocity equals initial velocity plus F net over m times delta t. So if force net is 0, then the final velocity and initial velocity will be the same, which is constant, which is also right here written in code. And then the new position will be the same, except we use the same velocity times delta t. And for delta t, we use a very small delta t, which is 0.01, because we want a small change in time to see far into the future. This will give us a more accurate info. And then this is going to be the graph of the model versus the experiment. So you see the model is the red line and the experiment is the dotted blue line. So you can tell that they're not the same, and the dotted blue line gets wider as time increases. And this is because it takes longer for the water bottle to get to this position at this time, and that's because the water bottle is slowing down. And this is because the net force is not actually 0 in real life. It's because there's like friction and air resistance slowing the water bottle down, because when you roll something, it will eventually stop. And this is also linked to Newton's first law. When an object stays in motion, unless another force acts upon it. In this case, that would be friction, force of friction, and air resistance. And to make the experiment like better and closer towards the model, you would need like a vacuum or like a frictionless table, so there's no like counter force stopping it. And you would also need like maybe like a perfect spherical ball, because my water bottle could be not symmetrical and like it's not rolling directly straight, so there could also be human error. So I would need like a machine to roll the water bottle. And that's it. This concludes my presentation.